The idea behind linear approximations is that while most functions are complicated and messy, linear functions are simple and easy. So here we're given just a function of x and y, and we're given some point, x naught, y naught. So we define the linear approximation of f at the point x0, y0, as you see here. So L of xy is also a function of two variables. Notice that these three quantities here are really just numbers. They're not functions. So they're values of a function or values of its derivatives. The only parts that are variable are these two. And they're linear with respect to x and y. So that makes them very easy to work with. So the idea is that L approximates f well for values of x and y near the original point. Now neither of those statements is very precise, what we mean by approximating well or being near. It's just kind of a general sense of how this is supposed to work. So one way we could quantify it is to let x minus x0 be defined as delta x, the change in x, and that's and y minus y0 is delta y. So those are changes in the variables from the original point. So if z is equal to f of xy, then delta z is just the change in f when you change both of those variables. So that's the actual change, and it's not so easy to compute depending on what f is. On the other hand, we approximate delta x by an infinitesimal quantity dx and delta y by an infinitesimal quantity dy. So these are meant to be small changes. And then we have an infinitesimal change in z, which is defined as the change in L. So this is approximate change. The idea being that even though it's only approximate, it's super easy to calculate with because it's linear. And if you substitute in what L is, using the different names of the variables for x and y, you get a simple formula for the differential, which extends the differential that we know from having just one variable. And this is called the total differential of z, or of f.